I was listening to Ellen here, and she had this very nice construction, probabilistic construction. I'm in a vacation mood, so I wouldn't dare doing that now. But maybe I'm a bit more over you, so maybe I regret that. And in particular, since this is an interacting particle system, a workshop, maybe I should have focused a bit more on that. But there is interaction. That's the main thing with epidemic models, both in the models, but of course also in reality, that the reason that an infectious disease spreads comes from individuals interacting. So it really is an interacting particle system. Although it will not sort of be evident in all my constructions as it was in Ellen's very nice overview talk, or not overview. Too much notation on this slide, but it will be less later on. So this is the introductory part. I don't know, probably some of you know a lot about epidemic models, but I guess some of you don't. So the simplest of all stochastic epidemic models, I would say, is the Markovian SIR epidemic. There's an even simpler one, which is the deterministic one, which this one will actually behave like if the population is large. So what is this? The SIR, I'm sure that by now many of you have heard about this. It's a model where you categorize individuals into three possible categories. Susceptible. Usually you assume that nearly everyone is susceptible initially. Then the I is infectious. Some people call it infected. I think that's a bad terminology because also when you have recovered, you have been infected. So I call it infectious, meaning that you're in the infectious stage. And after some time in the infectious stage, you recover. And when you have recovered, you are immune. If you want, in your model, you can later become resusceptible, but then that would be called the SIRS model. I think that comes in some later slide. Also, if you want to go into details, you can have a latent state. So you get infected, but not immediately, you don't infect others, so maybe you're latent for 3 days, so that is called an SEIR. Should be called SLIR, but E for exposed for historical reasons. So let these denote the numbers of susceptible, number of infectious, and number of recovered. So I'm talking about the SIR, so there is no waning of immunity here. That of course depends on what time scale you're interested. I think in the first wave of COVID, let's say the first year, it's a good enough approximation to assume that it's an SIR. I think now immunity wanes quicker, but also if you look in a several year perspective, you should have an SIRS model. So it sort of depends on the questions that you pose. And you start off in some state. Usually the simplest state is assume no prior immunity, just one or a few people infected and the rest being susceptible. It's a closed population. That's also, of course, not true in reality, but if you consider a few months or half a year, you can approximate the population to being fixed. But if you look at it like a 10-year perspective, that's of course not a reasonable assumption. And the model is as follows. So the simplest one, of course, assumes no structure, no community structure. But then later on you put in a structure that you know about. The simplest model assumes that we behave like molecules who meet each other completely at random. And a lot of the mathematics comes from statistical physics as well. So there are two parameters. Here is one, beta. That is, you can think of it, it is the rate at which you have close contact with other individuals, whether you're infectious or not. But it only matters meeting people when you're infectious. So it is the rate at which infectious people have close contact with other individuals. And close contact is defined as a contact resulting in infection if the other person is susceptible. So probably you meet that, let's say, 10 times this rate, but only 1 in 10 you actually infect someone. So beta is the rate of close contacts or infectious contacts. But it only results in infection if the other one is still susceptible, of course. Because if the other one is immune, then by definition you will not reinfect that person. And the other parameter is gamma, and that is the rate at which you recover. So the mean infectious period is 1 upon gamma. This distribution being exponential, but I don't even say that, but the assumption is that the infectious period is exponential. That's a very bad approximation. So it's used for mathematical purposes because then you get a Markov model. But the other extreme is to have a fixed infectious period, and I think that is a better approximation of reality than an exponential infectious period. But reality is probably somewhere in between, so quite often you model the infectious period by a gamma distribution, but also on the other hand, probably in reality you don't infect others at constant rate, but maybe you're slightly infectious in the beginning and then more infectious and then less infectious. So this model makes lots of simplifying assumptions, like all models in biology. Okay, how about this? So here are some results. I haven't sort of stated them as theorems, and I haven't proved them, but they have been around for between 30 years or something like that. And the first one is about the final fraction getting infected. So I defined the model now. Maybe you missed that. This was a definition. Each infectious person, while infectious, infects others at rate beta. Each time you pick a random individual whom you infect. So there is no social structures. And you recover at rate gamma. So if you view this model from someone who's initially susceptible, you realize that to remain susceptible for the duration of the epidemic, you must avoid these infectious contacts by the people getting infected. And this goes on, so maybe you start off with one person getting infected, maybe that person infects another one, so then there are 2 persons infectious, having infectious contact with others, and maybe 3 people get infected, then maybe someone recovers, so it drops down to 2, and eventually the epidemic stops. It will stop sooner or later, since we have a finite number of people and everyone can only get infected once. So after some finite, albeit random time, the epidemic will stop, and that is when there is no infectious person around, because when that happens, it can never sort of get going again. So that is the model. Questions about this model? Okay. If you could be interested in what happens over time, but maybe you could also be interested in how many will get infected at the end of the epidemic. Please note that there is no sort of changing behavior in this model, and there are no preventions and stuff like that. So if you're only interested in what is this? This is the number of recovered individuals at the end of the epidemic. You could have sort of the end of the epidemic, but of course after that nothing happens, so why not just consider a t going to infinity? And this divided by n, so this is the fraction getting infected. Then this has been proven that this thing here converges in probability, in distribution to a 2-point distribution. It has all in the limit as n tends to infinity. This random variable has all of its mass at 0, corresponding to a minor outbreak, or at another deterministic point tau. And actually I thought I would explain why, and this tau solves a certain equation. It is a solution to this equation. So if you solve this equation numerically, x equals 1 is a solution because we see that 1 equals e to the raised to the power 0, so that's a solution. And there's another solution if this quantity R0, which is this quantity, and what is that? That is the average number of infectious contacts you have, because if you have infectious contacts at rate beta during an exponential time, which has mean 1 upon gamma, this is the expected number of infectious contacts that you have during your entire infectious period. And if this quantity is bigger than 1, then there's another unique solution x to this equation. And why is that equation? What does it come from? This is not a proof to the equation, but it still explains it, at least I think so. So, tau is the final fraction infected. So 1 minus tau is then the final fraction not infected. So, as I tried to explain earlier, think of yourself, what is the probability that you avoid getting infected? So this is the probability of avoiding infection. I'm going to pull this down here. So, think of yourself. Maybe I was the first person being infected, so the probability that Ellen escapes getting infected from me is e to the minus beta, but I don't put all my infectious force on Ellen, I spread it over you, since it's uniform mixing, so it's beta upon m to Ellen, and then I do this for a duration, let's call it during my entire infectious period, and give me index 1. So this is the probability. Of course, this is random, so there probably should be an expectation. But this is the probability that Ellen avoids getting infected by me. But then if Ellen has to avoid getting infected by a lot of other people as well. For all people getting infected. So this k here, this is in itself random, and if tau is the final fraction getting infected, then n times tau is the number getting infected. So this k should be equal to n times tau. So we see that, well, now you probably see that this is here, and each of them are exponential gamma, so the mean, so it is e to the minus beta upon n, and then it is n times tau of these factors times the mean infectious period. And we see that this cancels out, and then there's a law of large number for the mean here, so it is e to the minus. The mean is 1 upon gamma, so it's beta upon gamma times tau. So see, 1 minus tau is equal to e to the minus. So this is exactly this equation here. Of course, this is not a mathematical proof, but there exists a mathematical proof of it. But I think this gives the main idea to this result. Questions? And then, if you're interested in the not only the final size, but the whole epidemic process, then what happens in the beginning is very different from what happens later on, because in the beginning it's actually, well, to start off, one infected person. You can never approximate that by something deterministic, and then there might be 2 or 3, so that's, you cannot approximate that by something deterministic. That part you approximate by a branching process. But if you want to cheat a little bit, you can say, okay, let me start with a positive but small fraction infected, and then you can approximate the whole epidemic process with the deterministic process, except at the very end of the epidemic, that you cannot approximate, but then very few people get infected, so sort of on a population level, it doesn't matter for determining how many that get infected. And what does it converge to? Well, it converges to this set of differential equation, and this is the simplest of all mathematical epidemic models. This is the SIR, the deterministic SIR epidemic. So it's just a differential equation. You can skip one of them because they sum to 1 and the derivatives sum to 0. So you can skip this if you want, but it says that the fraction of susceptible decreases at the rate beta times the rate at which susceptibles and infectious meet, and when this happens, they go into the infectious state, and infectious people recover at rate gamma. Okay? Here is a simulation. When R0 is 0.8, what I have simulated is, I show this slide to high school students when I talk, so maybe it's too simple for you guys. But anyway, here R0 is smaller than 1, and I've simulated an epidemic in population 1,000, 10,000 times, and all I've captured is saved is the final fraction getting infected, and we see that this agrees that all outbreaks are small when R0 is bigger than 1, but we see that when R0 is smaller than 1, they're all small, but whereas if R0 is bigger than 1, there's a 2-point distribution, small outbreaks and big outbreaks, and of course they're not all concentrated here, but when R0 is equal to 1.5, the numerical solution to this equation says 58.3%, and we see that the top of this normal distribution lies slightly below 600, so it agrees with this. And if instead I would have simulated the same number of simulations, but in a much larger population, so maybe 100,000, it should have said 100,000 here, and then you would have seen a much more peaky distribution here. So in the limit, you just get one spike here and another spike here. And actually, this simulation is not exactly from the model I described to you. It's from the discrete time version of it, where you infect every other one independently with probability p. That's called the Reed-Frost model. That you can approximate by the Elders-Reni network, actually. And in that particular case, the amount of probability mass here coincides with this number as well. Whereas the model that I described, you still have, so I'm cheating here. This simulation does not come from the model I described, it comes from a slightly different model. If I would have simulated from the stochastic SIR model, the peak would have been placed here as well, but some of this probability mass would have shifted over here. And here is, so this was 10,000 simulations, but here is just one simulation.
Sorry?
Yes?
So in the simulation before, was the initial infected site only 1 or?
1, yeah. If you start, that's a very good question. If you say started with 5 people instead, the location of this peak would have been the same, but the probability mass would have dropped dramatically, and nearly all of the probability mass would have ended up here.
So is it right that the splitting of mass comes from the fact that you have to survive the first period, and then kind of this ODE system kicks in that you're either in the state left or state right?
Yes, so the ODE system, you can approximate more or less not any model, but many models with the ODE system, but it's the probability of coming up to the initial phase that is much more fine, depending on finer details of the model. So this probability here depends much more, the stochasticity of your model affects much more how much probability is here, and much less the location of the variable. So here's one simulation in a population of 100, 1,000, and 10,000, and in each I plotted the deterministic differential equation system. So we see that in a large population, if you start with a positive fraction, it behaves very much like a deterministic system. So this was my very short sort of overview of epidemic models. There are a lot of things to be, so I will not cover everything, but what are people doing? What I said now was known maybe 30 years ago, so what are people doing now? Well, one thing is to consider different types of individual. That's quite often called a multi-type epidemic. Maybe you want to include vaccination and other preventive measures. Vaccination has been studied a long time. Other preventive measures like closing down societies, if I would have submitted a paper about what would be the effect if we closed down the society 5 years ago, they would have said, go to Hollywood and write a science fiction film about that. That's not for science. But now a lot of new research is going on about how to model it, and in particular how to estimate these different effects. Social structures is of course very important. Depending on what type of disease, households are known to be an important factor in spreading of aerosol type of diseases. If you're interested in sexually transmitted infections, then households are not, then quite often use network models instead. Extending these to when there is waning of immunity and introducing latent period is another thing that I haven't talked about much now. Having your model being dynamic, so new people entering the community, some leaving, and also maybe changing behavior over time, spatial aspects, mobility, and of course estimation of all these things. So there are a lot of things, even if I'm not talking about it, there are a lot of, it's not that everything is solved. And now I thought I would say a few words about 3 different problems that I have been working on fairly recently. And if I remember the schedule, I should finish at 11:45, is that correct? So this is my most recent work. It's with a Finnish colleague, Lasse Leskilä. Actually, it's not probabilistic at all, even if I come from with background in probability, so I think of things in probabilistic ways, but this model has nothing, there's no stochastic part. This is the simplest of all models, the SR model. So we considered a similar model with one little additional twist, which surprisingly has not been studied very much. And that is where we, over time, suppose we were God or we were prime minister of a country or something, saying that okay, now we have to reduce our contacts by a certain amount for the next 3 weeks, and then we'll go back to normality, or we reduce it more for 8 weeks or whatever. Suppose we could sort of determine this being goals. So this set of equation is the same as before, with the additional feature that we have this 1 minus p of t. So p of t, you should think of this as how much p is a fraction or or probability of proportion, how much we have reduced our contacts at time t. And suppose we decide this in advance. Well, our model is deterministic, so we know what will happen in a sense. But suppose we decide that, okay, this is our preventive strategy to, from now up until infinity, or hopefully earlier than that, we have this reduction of our contacts. Then we get this type of model. And I've added this sub-index P everywhere because the solution depends on how this happens. And we will get the final size, which of course is no longer as explicit as before. Okay, of course, the best thing is to reduce for a very low, well, maybe there's a cost as well, but if we're only interested in reducing spreading, of course the best strategy is to reduce contacts very much for a very long period of time. That's of course quite reasonable. So, but suppose there is a cost of the prevention strategy, and we have defined the cost like this. So we assume that it is a linear cost. That can be modified. Maybe, this is academic paper, but maybe reducing by 30%, there is some cost, but is the cost twice as much if you reduce it by 60%? Probably not. Probably there's a more cost the further down you go. So maybe you could have a square here. But anyway, we have looked at the linear cost. We're not claiming that's the correct thing, but that's what we have. So then we have an optimization problem. Which strategy with a cost bounded by some, say that we cannot close down society completely, so you have this cost to spend, and we want to minimize the final number getting infected. There are several criticisms to this model. For instance, the linear cost. Another thing is that we are considering time up to infinity. So maybe if we know that a vaccine will come in a year from now, that's a different story. So we see no sort of other thing that will help us in the near future. In reality, you might be less worried, let's focus on the first year, and maybe after that we are saved by a vaccine or something else. That's not the problem we have been studying. So we look up until time effect. Okay? So which strategy minimizes the final fraction getting infected among those strategies that have an overall cost not exceeding some constant C? So here is this the original model, the SIR, deterministic SIR model without any control. So this is the solution to the original set of differential equations. And here I've plotted 7 different suggested preventions, all having the same total cost. So strategy 1 says that have a complete lockdown for, I don't know what time this is. Let's say that this is 1 month. So start off with a complete lockdown for 1 month. That's strategy 1. Another one says do nothing and wait up until 5 weeks and then introduce a 1 month complete lockdown. Strategy 3 says wait even further. Strategy 4 says let's have a 50% lockdown during these 2 months. 6 says 25% lockdown for 4 times as long. And here is a time varying lockdown, and here is one start with a complete lockdown and then gradual. You can make up many other strategies. You can have a 2-week lockdown here and another 2-week lockdown here. So there's a huge class of lockdowns that you have to consider optimizing over. So the question is, which is the best of these strategies? And I will tell you the solution at the end of the talk. But if you get bored by the other topics, you can think of what you think is the best strategy. The next one is a paper that we wrote a couple of years ago, actually in the the spring of 2020 when we had this epidemic. I will not go into that much details, but first a very classic result, and that is, suppose you vaccinate a fraction V before the epidemic, then, and let's assume that we have a perfect vaccine, so you get 100% immunity forever, or for the time of interest. Then, if you do that, you get a new reproduction number, which you can index with V being the fraction that you have vaccinated. And this is the old one multiplied by the fraction that is not vaccinated. So suppose R0 is 5, and if you vaccinate 20%, it means that I no longer infect 5 people on average, because on average, one of them is already immune, so the new reproduction number is 4. So 1 minus V is the fraction that is not vaccinated. And you want this new reproduction number to be smaller than 1. That's the reason for vaccinating. So you want this to be smaller than 1, and this is a very simple equation. So put this, this should be smaller than 1, and then you solve this equation for V, then you get this. V is 1 minus 1 upon R0. This is probably the most important result of all in epidemic modeling. And it says how many you have to vaccinate in order to obtain herd immunity. This applies to childhood diseases. For instance, measles has an R0 which approximately equals 15. Of course, it varies in different countries, in different cities, whatever. But of the order 15, so 1 minus 1 over 15 is 14 divided by 15, and that is 93%. And this is the equation which, at least in Sweden, says that each year we want to vaccinate at least 95% of the newborns to be on the safe side. So this is actually not only academia, this is something that is used in reality. So this is the critical vaccination coverage. And if you vaccinate more, you obtain herd immunity. However, this is true also if you have a multi-type epidemic, if you vaccinate people on average. So if you have a multi-type epidemic, you have different, some people are more susceptible, some people are more infectious if they recover, and maybe people meet at different rates depending on age structure. Also in that situation, if you vaccinate uniformly, then the same result applies also to this model, except that R0 is a much more complicated expression than that. Then it is the largest eigenvalue to a certain matrix, but the new reproduction number relates to the original one in the same way. And at least in Sweden, we heard during the first wave that R0 is 2.5, which means that herd immunity will be reached once 60% have been infected. That was not what we aimed for, but there were questions, how many will get infected before things start slowing down? Well, since R0 is 2.5, this will happen after 60% have been infected. Too much text on these slides, I'm sorry for that. It has also been known for a very long time that you can do better than vaccinating uniformly. Suppose you know some people are more susceptible, other people are less susceptible, some people are more socially active, others are less socially active. Who do you think you should use the vaccine on, the socially active or the socially inactive people? Who would you use the vaccine for? The active ones, yes. So if you do that, if you vaccinate like that, you probably don't need to vaccinate 60% to reach herd immunity. I'm taking the example, suppose R0 is 2.5, if you would use your vaccine in a better way, you need to vaccinate fewer people than 60%. Do you agree to that? Okay. That has also been known. There are a lot of papers about optimal vaccination strategies and stuff like that. However, what has not been considered before, that was, okay, but now we have an outbreak going in a heterogeneous, so maybe a multi-type epidemic model is a good approximation. So it runs in this community, let's say Sweden, and suppose we sort of are able to stop the epidemic at some stage by maybe introducing preventions or whatever. So suppose after 60% have been, or no, what should I say? As the epidemic evolves in Sweden or in Germany or whatever country you are, who do you think will be infected mainly? Is it the socially active or the socially inactive people? Yeah. Probably a bit of both, but probably the socially active people will be overrepresented. So immunity spreads not as good as the optimal vaccination version, where you only vaccinate the socially active, but immunity spreads sort of to our favor compared to uniformly vaccinated. So this means that probably herd immunity will be reached earlier than 60% getting infected. Do you understand this sort of heuristic reasoning? Yeah. So that is something which we realized, which I think was one of the most exciting days of my life. But then we put this into a model. Let's see if I have. Yeah. So the susceptible and the socially active will be overrepresented during an outbreak, so that the immunity level to reach herd immunity should be smaller than this expression. And of course, how much smaller? So this was the nice insight, but then we want to say, okay, how much, is it 1%, then it doesn't really matter, or is it lot, is it a big difference or small difference? Of course, that depends on what model we use. So then we took a toy model. The only one thing realistic was that there are these contact matrices, social studies, where they have studied how much children interact with children, how much children interact with different age groups and different combinations. So that is taken from a social study. So I think we took one such study where the age groups, where there were 6 age groups. So there is information about how much the different age group mix with each other. So that was used sort of from an empirical study, but then we had an additional sort of just assumption. Okay, within each group, we categorize individuals into 3 categories. The normally socially active, and then some that are slightly less socially active, and some that are more socially active. And we said, let's say that 50% are normal, 25% are half as socially active or twice as socially active. So the mean does not equal this normal, but that does not. So this we did for social activity, and we did it also for varying susceptibility, but we assumed that these 2 were independent. So we categorized individuals into different age groups, but also how socially active they were and how susceptible they were, and also if they were infectious, how infectious they were. And we had 3 categories of each, and we tried to sort of calibrate this to the outbreak that we observed. And we came to the conclusion, we don't claim this is true, but sort of to get an idea of how big difference is it. And for this particular model, rather than having herd immunity at 60%, it would happen around 40 to 45%. So at least we thought this was a fairly bigger difference than we had expected, let's say. Here, this is illustrated in this heat map plot. So let's see now. here is the vaccine-induced immunity. So blue is herd immunity. What is here? Here is the, depending on what R0 you have, and this is the level you need to reach herd immunity. So when R0 is 2.5, we follow this line and get to 60%. Whereas if the immunity came from disease spreading in our model, it would look like this, and then 2.5, we go down here. Oops, 2.5. I think it was 41% or something like that. So a fairly big difference. Okay, I think that was it for now. So questions about this? Yes, let's take. Now you start with you. Yes.
You first?
Yes.
Thanks. So this model aims to minimize the number of the infected.
No. I started off with a slightly different talk, different topic, and I will come back to that later. So this prevention thing, when to put in prevention, I have not talked about the solution to that one. So this was a different problem, and the problem we studied here was when will herd immunity appear if the disease spreads in a heterogeneous community?
Yeah, it's a similar question though. You ask, how do we have to distribute the vaccines among the different types of individuals?
Well, when a disease spreads in a community, immunity comes from disease exposure rather than vaccine. But if you want to distribute a vaccine, I would say that that is a slightly different problem in the sense that then you have more liberty to choose whom to vaccinate, whereas now we're sort of studying what happens if a disease spreads in the community.
Oh, okay, then I will have to think a bit more about this model. Thank you.
Okay. Yes?
So you spoke about socially active people and
Sexually active?
no, socially.
Yes. Yeah, I did talk about sexually active, but that was when we talk about networks, but COVID, it's social active, yes.
Yeah, maybe somewhat correlated, but I was wondering, how do you model the socially active being? Like, do they have a higher rate of?
Yeah, that's a very good question. So we assumed that we have this contact matrix saying that kids, I don't know, but maybe kids spend 20% of their contacts with other kids, and then 10% with teenagers and 20% with. So we have this contact matrix, and then we assume that both the socially active kids and the socially not so active kids spread according to the same percentages, but the socially active do it at higher rate.
So it's okay.
So that is an assumption, maybe.
So it's not spatially.
Yeah, sorry, proportionally.
Yeah, it's not spatially in the sense that you have like a spatial structure.
No, there's no spatial structure here. Good comment. Okay, then my third topic, which is a little bit more complicated, so I will maybe not talk as much about it. This last line is very important, I think, because this is the equation that is used for estimating the daily reproduction number for COVID, let's say, in all countries, more or less. So let me try to explain what it is. So far, I mainly talked about different models and R0. So R0, I would say, is the most important parameter of an epidemic model. The second most important quantity of a epidemic model is a stochastic thing, and that is called the generation time distribution. This is a distribution, and it should always be a distribution. It should not be deterministic. And what is that? Well, it describes the time between getting infected and infecting others. So there are a lot of similarities between epidemic models and branching process models. So the terminology is used, the generation time, it's giving birth, but giving birth in this application is infecting others. So a lot of theory comes from branching process theory. By the way, in the model I described, which we call the SIR Markovian epidemic model, then for that model you can compute what is the generation time, and it happens to become an exponential distribution, which is, I forgot, it's independent, the generation time distribution is a difference, is exponential with parameter which is a difference between the infectious rate and the recovery rate, if I remember correctly. But you can compute it for different models, you can compute what is the generation time distribution. Or compute, either numerically but also analytically. If you have discrete time, which you typically do when you want to do things empirically, then it is a discrete time distribution. Probably day is your time unit, but of course in reality it is probably something continuous in time. And this daily reproduction number, that is something that varies over time. I'm sure you've seen this in your countries. What is the reproduction number now? So the model, which actually comes from an Euler-Lotke equation, which also stems from branching process theory, says that how many I of t is how many that get infected today, or you can think of how many that get reported today, whatever. How many get infected today? Well, that depends on what is the reproduction number now, but it also depends on how many were infected some days ago. But how long back in time should we look? Well, that depends on the generation time distribution. So if the generation time distribution is approximately 1 week, let's say 6, 7, and 8 days, then how many get infected today only depends on how many were infected 6 days ago, 7 days ago, or 8 days ago. So, but you scale up according to this generation time distribution. I thought I saw a hand raised. Okay. So this is what is used for estimating. So what do you know? Well, perhaps you know the generation time distribution. Suppose you know this distribution and you observe the reported number of cases over time. Of course, the best would have been to observe how many people that get infected, but that's hard. But the second best is a proxy of it, and that's the reported number of cases. Then you get sort of if you have this up until now, you can sort of estimate from this. If you have data on this and you know this, you can estimate the reproduction number for each day, and usually they make some type of smoothing so it doesn't vary too much. But this is how the daily reproduction number is estimated in your countries. But it assumes that you know what is the generation time distribution, and that is something that is quite hard to find out about. How do you estimate it? I think all papers I've seen about the generation time estimate were from China in the early phase of the first wave, and that was estimated, like it nearly always is, from what is called contact tracing. So you find infected people and try to find out. You ask them, have you met someone with severe coughing? Well, yeah, I met someone 5 days ago, and then you make a note of that, and then you find another case, and I met someone 4 days ago and another one 8 days ago, so then you don't know who was infected. And probably some people say, I don't know. So that is a problem in itself, but it is usually done using contact tracing. So here is a paper that we wrote before the pandemic, and this was inspired by Hence, it was not inspired by COVID, but it was inspired by the Ebola outbreak in West Africa. And one problem with this contact tracing, the problem with contact tracing is not that you look forward in time, but you look backwards in time. Of course, if I get infected today and I infect someone 5 days later, if I ask that person who infected by me, that was 5 days later, whether you look backward or forward in time. But the thing is, if you have an exponentially growing situation, then there are actually more possible infectors just a few days back than further back in time. So that will bias your estimate. So in a growing epidemic, short generation times will be overrepresented. Also, times of infections are not observed. Usually you don't observe when people get infected. What you observe is when they start showing symptoms. Usually that is, so you would like to know the time between an infection, me getting infected, and I infecting someone else, but usually you have the onset of symptoms, so that is a delay in both ends. So the mean is the same, but if you add a delay in both ends, the variance will become bigger typically. So you will have a correct mean, but if you estimate it from these shifted things, you will have a larger variance. And in this Ebola study that we looked in, there were quite a lot of data where they had not only one possible infected, but 2 or 3 or something like that. And the easy way out is, of course, to throw away those data points, which they did in that analysis, which was published in New England Journal of Medicine, so very high impact. So they threw away actually 75% of all contact traces they threw away because they had multiple infectors. So they only kept the ones when they had one single possible infector. But of course, it's never good to throw away 75% of your data. But the problem is that the ones that you keep will, if you have a sort of think about it and have a mathematical model, they will typically be shorter than the average contact, because if you would have a long duration, it's more likely that you would have had another contact in between. So the short ones will be overrepresented. That you can show in a model. So we looked at these rings. Here, these will be shorter from this effect. From this effect, they will have a correct mean, but a larger variance. And here, this last thing is that they will also become shorter. And then we try to sort of formulate this into a model. I will skip the details, but the conclusion was that we think that R0 was underestimated by approximately 25% if we combine all these things. And then one word about the paper where actually Martina here is the main author. There we sort of extended this a little bit, but also put it into other preventions. So the first paper I talked about now was the problem with estimating the generation time. We saw several problems, and actually all of them resulted that R0 would be underestimated. All were in the same direction, unfortunately. But now we looked at this generation time for COVID, and then we addressed a slightly different problem, and that is these COVID estimates from the early pandemic, part of the pandemic, was taken before there were preventive measures. So that was the generation time before there were preventive measures. But what happens with the generation time if you start having preventive measures? Then we looked at different preventive measures. For instance, if you contact trace, or if you screen, and probably a few others, if you encourage people to self-isolate, and if you test people, the typical effect is that you make the sort of the effective infectious period shorter. If you encourage everyone to, once you feel symptoms, isolate yourself completely, before that recommendation, people might not have isolated, so they would have infected a few people also after this. But if you either encourage or force people to isolate, that will, of course, it will reduce the reproduction number, but it will also shorten the remaining generation times. Ellen, you look questionable.
Yes. I was frowning because I just don't get that point. Why does it shorten the generation time?
Well,
Maybe
if you have before recommendations, you have these 3 generation times maybe, and maybe they have some symptoms here. So small symptoms here, maybe here, and maybe here. But then they have infections. Maybe you're infectious also before a little bit. So here, maybe I should have a circle here for symptoms. And then you have an infection here, but you have also an infection here and an infection here. Maybe you have just one infection here and here and here. But then, after, suppose you have the same outcome of 3 people, and then you say, isolate yourself completely. So what is the mean generation time here? It is this, that. Here you have 1 generation time, here you have 1 generation time, and here you have 1 generation time. Here you just have 1, and here you have 1, and here you have 1. So we have 1, 2, 3, 4, 5, 6 generation time, and the mean would be the mean of these 6 links. But now we erase the, you see, we erase the longer ones. We erase, now recommendations are, once you have symptoms, completely isolate yourself, then these 2 will be erased, and this one will be erased. So there will be fewer generation times, that is, reproduction number will be smaller, but also the remaining ones will be shorter. Someone raise hand.
I just wanted to ask you to raise the blackboard a little bit. It's very difficult to see for.
I can't hear what you're saying.
So just wanted to ask if you could raise the blackboard.
Oh, sorry. That's a good comment. So you have these generation times. Before there were no recommendations, all would result in infection. But then imagine that later on there was the same generation time, but now there was strong enforcement to once you have symptoms, you isolate yourself so you don't spread the disease. Then some of these will not appear, and the ones that will typically be short. So what we did was to sort of disentangle. So actually, this shortens the generation time. No, sorry, social distancing has no effect on the generation time. Because if you tell everyone to take social distance, that has no effect on the generation time. I can't go into details, maybe you can ask Martina afterwards, she's better at this. Self-isolation does shorten it, screening also shortens it, contact tracing also shortening it, but this one is the most complicated to analyze mathematically, but I will not show any of the analysis. But so what we did is we introduced these things, sort of using different parameters and stuff, and we tried to investigate how is the generation time affected. And then the important quantity is, okay, what if you use the original one taken from China in Wuhan before preventions? If you estimate R0, so if you estimate R0, or the current daily reproduction number, using this equation, but here where you use the generation time from before preventive measures, whereas in reality you now have a shorter generation time. What would be the effect? So that is something that we try to investigate. And here was some, of course we don't know all these quantities, so here was one. So we see that it makes a big difference. We had some specific choices of parameters where if we use the wrong thing, we would get 3.9 for the estimate of the reproduction number, whereas in fact it was 1.45. So it did make a big difference. I think I will skip any details from that. So the conclusion is that if we estimate R0 using early generation time distribution estimates, these estimates will be biased from above, or more actually biased away from zero. So if the true estimate is, if the true R0 is, let's say, 3, our estimate when we do the incorrect choice of generation time distribution, rather than 3, it will be biased from above, so maybe it will be 4, we estimate it to 4, whereas on the other side, if we're in the subcritical case, it will also be biased away from 0. So if the true value is 0.9, maybe we will estimate it to be 0.8. Sorry for skipping all the formulas, but that was the conclusion, and I think my time is out, so should we quit, or should I tell you what is the best solution to this first thing? All right, so who has a guess? So this is the outbreak without any control. So the question is when. We have an amount of preventive measures that we can place here, 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 here. Or depending on how long, if we put the massive lockdown or not, or should we have a sort of lockdown, normality, who wants to guess? Please remember that it is under the assumptions of this very simple model, and there is no scope for a vaccine arriving at some time. Yes?
I think usually they say that early prevention is the most effective one, so.
Early prevention. Here is the best one. Do nothing until this peak has been reached, and then put in a massive lockdown for as much time as you have. So very counterintuitive. I will show 2 more slides. This is the infectious curve. The black one here, this is the uncontrolled, sorry. So the black one is this blue one. So this is the incidence over time if we do nothing. Here is just a cumulative number, so this is the number of infectious or recovered individuals. So this is the cumulative number. Here are 2 prevention strategies. The blue one is the one that is best under the additional assumption, which I think is quite realistic. Suppose it's not possible to have a complete 100% lockdown. Suppose the best we can do, or the most of lockdown we can do, is 75%, just by arbitrary choice. If it's 75%, you should start slightly before the peak. You see that, but not much before the peak. If this is days, I think it's 3 days. So if we can lock down society for 75%, if we only want to minimize the total number infected, we should wait very long and then put down this 75% lockdown for as much time as we have. The effect is that rather than seeing this black curve, we will see this blue curve. So of course, before we do nothing, it coincides with the black curve, but then it drops quite quickly. And we see that it's a fairly big difference, but not a huge difference, but a fairly big difference. A very different optimality criteria, but perhaps better, I don't know, that is to not minimize the total number of people getting infected, but minimizing sort of the peak prevalence. The best strategy for that, which has been derived by other people, says to start a bit earlier than our optimality criteria. So start after, I don't know if this is 17 days. Of course, this is just for some arbitrary chosen numbers of things. Don't go up as long as you're allowed to, but for this particular, I think it was around 60% lockdown, and then gradually lift lockdowns up until here. And then and the gradual lifting is such that we stay at the same prevalence for a long time, and then we drop it. So we see that, of course, this is very different. So the hospitals probably would be higher than this, happier with the red solution. But maybe the people working in the cemeteries, maybe they would enjoy our thing better, because that's how much people that would die, how many people would get infected is probably proportional to how many that would die. So we see that in the end, the red one actually has more case fatalities than the blue one. My last slide is the perhaps most surprising of all slides. So if I was a consultant, they said, Tom, quickly find the best solution. When should we have the lockdown? And I would come and what do you want to minimize? Do we want to minimize the total number infected? I would say, okay, do nothing for the first 23 days. Do nothing for the first 23 days and then put as much lockdown as yet. I'm quite convinced that they will say, no, we can't do that. Maybe they say, I will give you 1 more week. So, okay, I don't trust you. I will give you 1 more week. So we start the lockdown here instead, 1 week earlier. But we keep it for the same time. So I said, this is the best. No, we don't trust you, Tom. We give you 1 more week. So you get your best strategy. We put 1 more week of prevention before that. So this, sorry. So here is this new strategy. You have myriad, but you add 1 week before also. It will look very different. We will get this red curve. So of course, if we put in massive lockdown here, we will start seeing decline here. But the problem is that once we lift here, there will be, in total, not many people will have gotten infected. So we're far from herd immunity. So we'll see a big second wave. So the total number infected will be close, at the end of the outbreak, will be close to doing nothing. And in particular, it will be much bigger than this strategy. Of course, this is a toy model, so I'm not, but still, it's quite counterintuitive. Adding 1 week prevention before can actually be harmful in the sense that you get more people infected at the end of the outbreak.
But did you check what happens if you decide to minimize the averaging time or the number of infected individuals instead of the size of that compartment at the end?
I didn't.
So let's say that instead of minimizing I at the final time, we want to minimize the averaging time of I. So we want to keep low the average number of infected individuals over a certain time window.
The average number, I think that coincides with what we do.
You are minimizing the final number.
But if people are infectious for...
Because typically in this type of optimal control problem, so what happens is that in that case, instead of waiting and then shooting, you apply the control at a lower level constantly.
Okay, I haven't thought of that, so the honest answer is that I don't know. Anyway, I am done, and I forgot to show off a little bit, and the show off is that this thing about herd immunity was published in Science, and I've never published there before, and I probably never will again. All right, thank you very much. Sorry for talking too long.
No, thank you very much for your interesting talks. Were there other questions? Okay, you.
Yeah, so I was wondering how flexible is your approach of computing this optimal prevention strategy? Like if I were to give you an arbitrary cost function, then would you be
I don't know if it's illegal, but can you remove it just when you talk?
So I was wondering if how flexible your approach of computing this optimal prevention strategy is. If I gave you some arbitrary cost function, would you be able to at least numerically compute the optimal strategy?
Yes, so I think if you add sort of multi-types, the question was about this last thing, how to optimize prevention. If you add realism in terms of multi-type setting and so, I think that will have marginal effect. Whereas if you put in a different cost function, I think it will have a fair effect. Of course, it depends on how different your cost function is to this linear cost that we added. Another thing that will have a big impact was if we picked our time horizon not to infinity, but not so far ahead. So if we think that the vaccine might arrive in half a year from now, then that could have a big impact.
Thank you.
Do you have an intuitive explanation of the counterintuitive result that you showed?
If I have an intuitive explanation, yeah, the explanation is that if we don't think something will save us, like a vaccine, and if we're not prepared to change our life forever, then the only way out is to reach herd immunity. And with this strategy, so we should reach herd immunity. We will reach herd immunity eventually, but the problem is here that not many people will have gotten affected, and if we lift restrictions then we will see a big second wave. So you sort of want to lift these restrictions more or less when you have reached herd immunity, because if you're far from herd immunity when you lift the restrictions, you will see a big second wave. But by the way, one more thing that would change things rather dramatically is adding seasonality, because then you can sort of relax, and that's what was done in 2020. Once the summer came, it was all right to relax preventions because other factors reduced. So seasonality will change matters quite.
I think just a comment for this. I think one reason for this is actually that you already reached a state where you have a positive fraction in the population, and so you cannot stop the whole infection now. So even after your lockdown, you will still have some infections left, and then the second wave comes because you will not prevent everyone getting infected. So you have not the option of having in the beginning killing every infection, because you already have this deterministic limit.
I have actually two questions. One related to the last one. Getting the optimal strategy, is that in some way equivalent to maximizing the number of individuals that reach resistant state or recovered state during the lockdown? Or is it rather stopping at the time, as you just explained, stopping at the point where you reach herd immunity? And the second question is, really unrelated. If you have multiple variants competing for susceptible individuals at the same time, how would that change the picture, or doesn't it? Because you're already still in this branching process approximation where it doesn't make a difference.
Yeah. So the first question I sort of know, so let me address that one first. You want the lockdowns to prevent a lot of infections. That's your purpose with the lockdowns. And when there are a lot of infected people around, if you lock down then you really are preventing a lot of infections. Whereas if you lock down when there are only like 5 people infected, you're not preventing that many infections. Sorry, one more thing that will change things is if you have a stochastic model, you might, by a dramatic lockdown, be able to make the epidemic go extinct. In a deterministic model, that will never happen. It will just so that depends on if you are able to isolate the country afterwards. Then that could be an effective strategy. Probably that applies more to sort of islands or those type of countries, whereas less to democracies in Europe, where it's very hard to stop the war.
Well, New Zealand was close to that, right?
Which one?
New Zealand was
Yes,
close to that.
yeah, I think so. Your second question was different variants. There is quite a lot of research in different variants and how they take over. But then you have to sort of specify, do they compete against each other? Do they give partial immunity or complete immunity to each other? So I wouldn't dare say sort of any general comment to that, how it would affect the result.
So other questions?
Just a quick question. The N infinity constraint on P in this the maximum value that P could attain in this
we picked
one.
Yeah. So if you can have a complete lockdown, then you should wait until the peak. If you're not allowed to have a complete lockdown, then it will always start before the peak. So if 75% lockdown is the one that just a numerical example we picked, so then it was slightly before the peak, whereas if you're only allowed to have, let's say, 50% lockdown, you would start this 50% lockdown slightly earlier. Maybe that was not your question, but...
No, I was rather wondering, because here in the scheme you have that the value of P, which is constant, is equal to 1, whereas in the numerical simulations it seemed like to be 0.8 or something, so... on the next slide, probably. Yes, the blue line.
So this one we said it is only so we modify the problem and say among all prevention strategies that never exceed a 75% lockdown.
Okay, I see. Okay.
Then the best solution is to actually use a 75% lockdown. So you always should go up to what is possible, and then you do this for constant period.
Yes, so actually the control saturates on that window. Yeah. That's what I was asking. Okay, thanks.
Some other questions? So I have a question.
Yes.
Are there stochastic models that take into account the presence of the viral load? So, in like a meter in the infection rate?
Yeah, I mean, there are models where you have a time-varying infectious rate. So 0 is when you get infected. So then you can sort of think that either you have a deterministic curve, maybe something like that, or more likely we have a stochastic curve, because what happens in your body is probably not the same. So you have a sort of stochastic process with some law around it. So there are models for that. And if you have prevention, it really matters if things don't change over time. What really matters is the expected value of this integral, because that will be R naught, more or less.
Okay.
So it depends on sort of what you study when stochasticity comes in.
Thank you. So, if there are no other questions, then let's thank Tom.